last lecture what I was talking about. In the last lecture, what I... Something like this with sodium ethoxide and then with some alkylating agent, let us say ethyl iodide, what you will get what you'll get is a compound like that, as I showed you yesterday. And if you hydrolyze this with alkali, you get the sodium salt. And if you treat that with acid, you then get the corresponding carboxylic acid. Finally, that is heated. It loses carbon dioxide and you end up with that ketone. So that's just an example I must have given you yesterday, almost the same example. It's an example of using a beta ketone ester or a beta dicarbonyl compound, because if you count this as one carbonyl, that's the alpha position, that's the beta position. So there are two carbonyls. If you take a beta dicarbonyl compound, it's very easy to deprotonate it with sodium ethoxide, and the resulting carbanion reacts with an alkyl halide via an SN2 process to attach the alkyl group to the alpha position of the beta dicarbonyl system. And then one can get rid of this first by hydrolysis with salt, then conversion to the carboxylic acid. And you know, because I've told you previously, that if you have an alpha beta keto acid and you heat it, it loses CO2. And so what's left is just this bit. So you can make an unsymmetrical ketone in this way. If you took this compound, deprotonated it, and then alkylated it again, then you get, at the end here, yet another alkyl group. So there are various modifications one can make of that. Well, that's the end of everything that I wanted to say about dicarbonyl compounds. I want to change now to the second last subject, which is amines. These are all derivatives of ammonia. Right here in the last lecture, I wanted to put up these two, but I have forgotten what the corresponding addition numbers are. You should try these as a homework exercise.
After the stairs thing? After you said, are you coming down? Yeah. I need to do a follow-up.
Very simplest amine, of course, is ammonia, but we're not interested in that compound, we're interested in derivatives in which the nitrogen is attached to carbon. And the simplest example is that compound, which has two names. It's either methylamine or methanamine. Now this is the formal name, and you can see just how that formal name is derived, because there's one carbon, and the hydrocarbon that corresponds to one carbon is methane. And if you cross off the E and add amine to what's left, you get the formal name. Likewise, this compound is ethylamine, or methanamine. This one here, let me explain the name to you. If you go back, methylamine, you name the carbon piece that's stuck onto nitrogen, this one ethylamine. This carbon piece is an isobutyl group. Why butyl? Because there's 1, 2, 3, 4. Every carbon piece that's got 4 carbons is butyl. It might be butyl, isobutyl, tertiary butyl, cyclobutyl, but they're all 4. When a carbon chain ends in 2 methyl groups attached to the same carbon, you use the word iso. So this butyl because 4, iso to tell you the arrangement of the atoms. The arrangements are such that at the end of a chain, there are 2 methyl groups stuck on the same carbon. So this is now counted for 3 carbons, the 4th one is there. So this is isobutylamine. However, if you want to name it in the formal way, then you choose the longest chain that has the nitrogen attached to it. That's 1, 2, 3, or 1, 2, 3. So, because it's 3 carbons, you think of propane, cross on the D, and add amine, so it's propanamine. Now, where in the propane skeleton is the amine group? It's on carbon 1. But we notice that on this 3-carbon system, at position 2, if that's 1, at position 2, there's a methyl. So it's 2 methyl, 1 propanamine. That's how you derive that name. Similar way, this is called cyclohexylamine. Or cyclohexanamine, because obviously there's a cyclohexyl group carrying the nitrogen, and if you see a cyclohexyl group, you get the cyclohexane. You must cross off the E for cyclohexane and add the word amine. So this is cyclohexanamine. Now all these compounds that I've drawn so far are primary amines. And a primary amine means that the nitrogen is attached directly to one carbon. Doesn't matter what that carbon is further attached to. It could be attached to 1 million carbons. But so long as the amine is attached just to one carbon, and therefore carries 2 hydrogens, it is a primary amine. Now there's another class of compounds called secondary amines, in which the nitrogen is directly attached to 2 carbons, and therefore carries only 1 hydrogen. And I need to show you how to name those compounds. So let's have a look at a few secondary amines. So here is the formal name. It's N-methyl ethanamine. Now how did I get that name? Well, I noticed that the nitrogen is attached to 2 carbon pieces, and I identified the longest carbon chain, which is 2, and so I chose that as the reason for calling it an ethanamine. And then the other substituent, which is on nitrogen, is a methyl, so it's an N-methyl ethanamine. This name, I just realized that it's the derivative of ammonia, in which there's an ethyl and a methyl group. And I just put them in alphabetical order.
I think last time you asked me it's connected to the battery. Oh yeah, it's just attached. Just okay. So remember last time? Yeah, you wrote that. I wasn't sure either. Yeah.
So this compound is called N-methyl ethanamine, or it's diethylamine. Now finally, there are tertiary amines. And a tertiary amine is one in which the nitrogen is attached directly to 3 carbons, and therefore the nitrogen does not have any hydrogen on it. This compound is called triethylamine, or NN diethyl ethanamine. Now I perhaps need to explain to you how I get that name NN diethyl ethanamine. Now the first thing I should say is that this little underline underneath the N is just an instruction to a printer to put that letter in italics. So when you prefix the name by a capital N to indicate that what follows is on the nitrogen, that N is a capital and it's printed in italic font. Now, I have to choose the longest carbon chain that carries nitrogen? Well, it's not very difficult to do because all three carbon chains are the same, and it's a 2-carbon piece. And therefore, I would regard this as a derivative of ethanamine, which is just ethyl group attached to NH2, in which the nitrogen now carries 2 substituents. They happen also to be ethyl groups. So it's NN-diethyl ethanamine. You can understand why it's called triethylamine. If you have an ethyl group on nitrogen, that would be ethylamine. If you have 2 ethyl groups on nitrogen, to give a secondary amine, that would be diethylamine. And if you have 3 ethyl groups, it'll be triethylamine. Now, what happens if you have different substituents on the nitrogen? Well, this could be called ethyl, methyl, propanoamine. Sorry, propylamine. I beg your pardon, propylamine. So what I've done is I've identified the fact that the compound is an amine. I've realized that there are 3 groups on the amine. There's a methyl group, an ethyl group, and a propyl group. So I'm going to put those 3 groups in alphabetical order: ethyl, methyl, propyl, amine. The formal name, the International Union of Pure and Applied Chemistry name, first asks me to realize that the stuff is an amine. So I know that the name's going to end in amine. And then I have to choose the longest chain that carries the nitrogen. Well, the longest chain that has a nitrogen on it is this one. That's a propyl group. So this thing is a derivative of propanoamine. And it's an N-methyl, N-ethyl propanoamine. And you put those substituents in alphabetical order. So this thing is N-ethyl, N-methyl, propanoamine. There's one other, well actually more than one, there are a couple of other points you need to know. In naming organic compounds, it's often necessary to identify what's called the principal functional group. And sometimes a nitrogen substituent is the principal functional group, and sometimes it isn't. Now, when it isn't, you name the compound according to what the principal functional group is. And supposing the compound structure is such that there's a carboxyl group in there and also a nitrogen piece. Well, the carboxyl is then going to be the principal functional group. How do I know that? Because there's a list published by the International Union of Pure and Applied Chemistry, and it just gives you the order. Now, when you name a compound that has a NH2 or an alkylamine or a dialkylamine substituent, but also has another group that's a principal functional group, you need a word to indicate the nitrogen substituent, and that word is amino. So if you've got some acid, and somewhere along the chain there's an NH2, you'll name the compound as a carboxylic acid, and one of the substituents will be an NH2, which is amino. So it'll be a something amino, something or other acid. Let me show you how that works. name this compound, you realize that it's an alcohol and also an amine. And it turns out, if you look on the list, principal functional group is the alcohol. So this is going to be named as an alcohol. Now it's a 2-carbon alcohol, and so it will be some type of ethanol. 1, 2, and it is in fact 2-amino ethanol. This compound is clearly a carboxylic acid, and it's also an amine, a primary amine. And if you look on this list, which I'm not going to hand out, all you need to know is carboxyl is a very high-ranking group, and hydroxyl is higher ranking than amino. If you look on the list, you'll see the carboxyl is right at the top, and so this material is going to be named as an acid. Now it is a 3-carbon acid. And so a 3-carbon acid, say without this nitrogen, would be propanoic acid. Budget 1, 2, 3. But it is in fact 3-amino propanoic acid. So I've told you a fair amount about naming aliphatic amines. That is to say, compounds in which there's nitrogen on a methyl, ethyl, propyl, cyclohexyl carbon piece. And I've told you, given you a few examples on how to name amines in which the amine is secondary, so there are 2 alkyl groups on the nitrogen. And I've told you how to name, I've given you a few examples of naming amines in which there are 3 alkyl groups on the nitrogen. Now there's another type of amine in which the nitrogen is attached to a benzene ring. And those are named a little differently. This compound is called aniline, or benzenamine. So this is N-methyl aniline. I'll give you just a few. Many of these have trivial names. You can see that there's a trivial name, toluidine, but you can name it systematically by noting that it's a nitrogen stuck onto some type of hydrocarbon, which is benzene. So you take the name benzene, cross off the final E, and add amine. So that gives you benzenamine. And then if you count this as 1, 2, 3, 4, it's 4-methyl benzenamine. But it's commonly called toluidine. And there's one more. Para-anisodine, or xenamine. Now in all the, I should say that benzene compounds carrying the nitrogen are very, very important. Those compounds are used in the dye industry. They're used to make all sorts of dyes, used to make all sorts of medicines. So they're rather important. And one of them was actually used in the very beginning of the dye industry by somebody called Perkin. Perkin was I suppose the equivalent of a graduate student at Imperial College in London, and during one of the holidays, I think it was Easter, he decided he would try and synthesize a substance called quinine. He didn't know the structure of quinine, it wasn't known at the time, but he had an idea of the formula of quinine. He knew how many carbons, how many hydrogens, how many oxygens, how many nitrogens. And in those days, which was in the 1800s, the only sort of logical thing that you could think of was to take the formula of an amine and multiply it by 1 or 2 and oxidize it, which means take away 2 or 4 hydrogens and so on. And then you could come up with the formula of quinine. And so we took an amine and he oxidized it, hoping to get quinine. Of course, that logic is so weak that the chance of his getting quinine was sort of less than the chance of winning the 649 lottery. There was no chance at all. But he did get something. He got basically a mess. Being a good scientist, he was a British scientist. Being a good scientist, he found that this dark product that he got stained material, stained cloth, and stained it a very nice shade of light purple. And this it didn't fade very easily, it didn't wash out very easily, and various fashionable ladies in Europe adopted this coloured material, which was called mauve, and became very popular. And that was the start of the industrial dye industry, which then led to the pharmaceutical industry. So it turns out these things were very, very important. Now, all the things that all the amines I've talked about so far have got the nitrogen either stuck onto a ring or as part of a chain. But there's another type of amine in which the nitrogen itself is incorporated into a ring. And I just want to put up 3 examples. That's a substance called pyrrole. This is a substance called pyridine. And this is a substance called piperidine. Now you can see that piperidine is a secondary amine. For the simple reason that the nitrogen is attached directly to 2 carbons, and consequently the nitrogen also carries 1 hydrogen. If I were to replace this hydrogen by a carbon, say a methyl group, I then have a tertiary amine because the nitrogen would then be attached directly to 3 carbons. So when you're dealing with amines, you can have NH2 stuck on some piece, which could be a chain or a ring or a benzene ring, or you could have nitrogen carrying a carbon that can be stuck on a chain, carrying carbon 100 that's stuck on a chain or a ring or a benzene ring, or a nitrogen carrying 2 carbons stuck on a chain or on a ring or on a benzene ring, or a nitrogen can be part of a ring and then carry 1 hydrogen, or the nitrogen can be part of a ring and carry yet another carbon, so that's a tertiary amine. So there are all these possibilities. Now, what's the shape of these amines? Oh yes, before I forget, this big health session, which I booked for December the 8th. A couple of students came to me yesterday and said that they had just been informed that there was a lab that they had to do on that day. And could I change the time? And so I assume it's a chemistry lab, but I don't know for sure because I didn't inquire. So, you know, it'll be on the same day because that's the only day that's convenient, and it was scheduled for 1 o'clock. I could schedule it for 10:30. But then, what's that? 10? My cook doesn't arrive till 9:30 to prepare my breakfast. I'm not at 10. I can do it at 10:30 when I come in, if they'll let me have the room. I think they will. Let's have a show of hands. Who would like it 10:30 as opposed to 1? Who would like it at 1? The 10:30 wins.
I thought he was going to make it later, but made it earlier. Earlier's better.
I'll see if I can
get more of the day
I'll see if I can get the time change.
So you're like 4 hours.
Okay. Let me continue now with Then we continue. We might have to have a 5-minute break there because I want my lunch at 12. I don't want the caviar sandwiches to get soggy. Or the champagne to warm up.
So weird.
Okay, let's talk about the shape of amines.
It'll go by. Stop looking at the phone. But on the bright side, like when he's talking, yeah, like how awesome is that? It's exciting, but we still have to finish this before we can celebrate.
Well, it's really not that bad. It's good, but it's actually a lot of weight.
I heard it's like 45%.
So you just sit back and like get your ice bucket ready.
Okay, if you take a simple amine such as triethylamine, the shape of the nitrogen is more or less tetrahedral, but the thing is inverting very, very quickly. So that's one thing you need to know about the shape of amines. The shape is tetrahedral, but it's inverting very, very quickly. Another thing you need to know about amines is that they are basic. Now they're not as basic as hydroxide iron, then they're not as basic as hydroxide iron, they're not as basic as alkoxide iron, and they're certainly not as basic as a carbanion, as you might get in a Grignard reagent. But they are basic, and so if you treat an amine with acid, you will protonate it. salt. And the way that that has happened is that the lone pair on the nitrogen has attacked the proton. Now, I've told you about various types of amine, and the one type I want to draw your attention to is the aniline type. This one is less basic than that one. And the reason is that the nitrogen lone pair in the aniline can be delocalized into the benzene ring. You can write resonance structures. For example, I could move the electrons like this, and I could move them out onto that carbon. Whereas for cyclohexylamine, for that one, I can't do that. So in the case of cyclohexylamine, the nitrogen lone pair is fully available to attack an electrophile, such as a proton. Whereas in the case of aniline, it's not fully available because some of it is siphoned off into the benzene ring. And so aniline is a much weaker base than cyclohexylamine. The other thing you need to know is you need to compare the basicity of amines with amides. And amides are much, much less basic. Why should that be? Well, there are two reasons. Here's the lone pair on the nitrogen. So just like amines, amides do have a lone pair on nitrogen. And you might well expect that they would be basic. But they're nowhere near as basic as ordinary amines. Why should that be? Well, if this nitrogen is going to attack a proton, the ease with which this lone pair can, in a sense, leap out and attack a proton is controlled by a few factors. One of the factors is that a carbonyl group is electron withdrawing. And so there is an electron withdrawing inductive effect, making the lone pair less available. The other thing is that the lone pair is involved in resonance. And so this lone pair is really distributed over 3 atoms. It doesn't belong just to the nitrogen. Whereas in this case, it belongs only to the nitrogen. And so its full power, its ability to attack a proton, still exists. In the case of aniline, it doesn't belong totally only to the nitrogen, so it's less able to attack a proton. And likewise, in the case of amides, it doesn't belong totally to the nitrogen. So amides are weaker bases than amines. Now, from what I told you, you immediately can conclude that an amine should be soluble in dilute aqueous acid, because the acid will protonate the nitrogen to give you a salt. And salts are soluble in water. So if you have two compounds, one of which is an amine, and one of which isn't an amine, a very easy way of separating the two is just to shake the mixture with dilute acid, say dilute hydrochloric acid. The amine will dissolve, and the other thing won't dissolve. You can extract it out with ether. And then if you wanted to recover the amine from the acid, you would add base to the acidic solution to make it basic. And then you could extract the amine out with ether. That's a classical way of separating an amine from something that doesn't dissolve in dilute acid. Amines have a number of uses, and I want to tell you one of the uses now. There are a number of naturally occurring amines. Strychnine is one. Poison, of course, you've heard of it. Quinine is another one. That's a medicine, antimalarial compound. There are a number of amines that are chiral, naturally occurring, and they are isolated from a natural source as a single enantiomer. And these amines are used to carry out a process called resolution. If you have a racemic compound, say a racemic acid, and you want a single enantiomer, you just want one of the enantiomers from that mixture of equal amounts of the two enantiomers of the acid, you can do that by using an optically pure amine. And the optically pure amine that you can use is either quinine or strychnine, or there are several others, or you can use not naturally occurring amines, but optically pure amines. And I want to show you a very simple example of how you use an amine, an optically pure amine, to do such a resolution. Supposing I have these two hydroxy acids, and I want just one of them. What I would do is to take an optically pure amine, and one that's quite often used, is this one. So single enantiomer,